in principle, if you stay outside the event horizon of a black hole, right? If the black hole has a mass m, then there's a beautiful little formula that you can work out for how big the black hole is. You take 2, multiply it by Newton's constant g, multiply it by the mass of the black hole, and divide through by c squared. And that number tells you how close you can safely get to a black hole without being pulled in. And if you stay outside that number, 2gm over c squared, then in principle you can go to the black hole's edge, turn around and come back. And if you do that, when you come back, you will note that you come back to the future. If you spend time near the edge of a black hole, time elapses there more slowly. So clocks back on Earth will be ticking fast while your clock is ticking off time slow. So if you spend like a year hanging out near the edge of a black hole and then you come back to Earth, it might be 10 years in the future, or 1,000 years in the future, or 1 billion years into the future. So the journey that you're talking about may seem to be a journey through space. You go from Earth to the black hole and then you come back, but it's actually also a journey through time. Because when you go to the black hole and you come back, it will not be the amount of time that you think should have elapsed. It'll be much more on planet Earth. Einstein's relativity gives a very different way of thinking about time, in which we imagine that every moment is as real as every other moment. It's not just that the present is real and the past is gone, the future is yet to be. Every moment is as real as every other. Past still exists, future exists, present exists. And this is what gave rise to Einstein's own poetic description, where he said, the difference, the distinction between past, present, and future is only an illusion, however persistent. And we are so familiar with the fact that when you look out at physical happenings in the world, they seem to always unfold in one temporal orientation. And in fact, there's an intuitive sense that time has a direction. Time has what we call an arrow. Right? The canonical examples that we like to use, if you drop an egg, it splatters, but it never unsplatters. If someone dives off a diving board, they go into the water, but you never see somebody jumping out of the water, untumbling, and landing on the diving board. And that's an important fact, because when you see reverse run films, the reason you laugh is because it's so ludicrous relative to your understanding, your intuition about the nature of time. But here's the amazing fact. When you look at the laws of physics, as currently configured, all laws of physics, when properly interpreted, so I won't go into the nuances of that, but all laws of physics have the quality that they treat the future and the past symmetrically, identically, on equal footing. Which means when we physicists study the laws of motion, any sequence of events that can unfurl in one direction, the reverse sequence is allowed by the laws of physics. And in fact, there's an algorithm for ensuring that if you have, for instance, any physical unfolding, if you want to reverse it, all you need to do is reverse the motions of the particles that are involved. Near the vicinity of a black hole, and if you don't understand this, it doesn't matter. We can put down a space-time diagram, if you remember from high school. This is where we have time on this vertical axis, and you set off a beam of light that fills out a cone, so-called light cone. And what happens is the geometry of space and time is so distorted by a black hole that beyond what's called the event horizon, the direction of time and space is so twisted that as light propagates, it cannot get out of the edge. It cannot go beyond the event horizon of the black hole, and that's why no light can get out. That's why the black hole is black. If you are near a waterfall and you are, say, paddling your kayak, if you can paddle faster than the rate at which the water is flowing toward the waterfall, you can get away. But if you can't paddle faster than the water is flowing, then you can't get away and you're doomed to fall down the waterfall. And here's the idea. The analogy is space itself falls over the edge of a black hole. It's sort of like a waterfall of space. And the speed at which space travels over the edge of a black hole is equal to the speed of light. Nothing can go faster than the speed of light. So near a black hole, you're doomed. So you might as well just paddle right toward the black hole and go on a joyride down the throat of the black hole itself. So that's another way of thinking about it. Edge of a black hole, event horizon. Space, in some sense, is flowing over the edge. It's flowing over the edge at a speed equal to the speed of light. Since nothing can go faster than the speed of light, you can't paddle upstream. And if you can't paddle upstream, you can't get away from the black hole. You're doomed and you will fall into the black hole.
Time is not the same. It's not universal. It depends not only on how you're moving, it depends on the gravitational field that you are experiencing. If you were to go near the edge of a black hole, where gravity is much stronger, then the time warp associated with being nearer to the black hole versus farther from the black hole could result in a significant time warp, time difference between clocks that are ticking at those different locations. And of course, there have been examples in popular culture that have made use of that scientific fact. Interstellar, right? So in Interstellar, if you recall, there's a black hole and some of the astronauts go relatively close to that black hole, and that affects their passage of time. And just to remind you, Kip Thorne, who was the science advisor and had the initial idea, I believe, for this film, made sure that everything was as scientifically accurate as it could be. So this is an example where just a few hours, according to Matthew McConaughey, translates into 23 years up on the mothership, because time is elapsing so slow in the powerful gravitational pull of a black hole relative to the rate at which time is elapsing elsewhere.
The Sloan Digital Sky Survey did a wonderful study of a vast number of galaxies. It seems to be a ubiquitous quality that black holes are at the center of galaxies, and those are typically gargantuan black holes, millions or billions of times the mass of the sun. Some have suggested that early stars, which were quite large compared to more modern stars, when they exhausted their nuclear fuel and they collapsed in on each other, they created black holes that were large, and then they continued to suck in more material from the environment, and they grew larger and larger still. So that's sort of one rough way that people think about how these massive, enormous black holes may have formed, but it's uncertain. LIGO, this Laser Interferometer Gravitational Wave Observatory, gravitational waves. It took headlines a few years ago when it detected the first ripples in the fabric of space. It detected them from two black holes that were 1.4 billion light years away, like 1.4 billion years ago, rotating around each other, going near the speed of light, slamming into each other, creating a tidal wave in the fabric of space that rippled outward at the speed of light. Part of it raced toward planet Earth. There wasn't anybody on planet Earth to see it at that moment, but it had 1.4 billion year journey to traverse. It raced toward planet Earth. When it's about 100,000 light years away, it grazes the Milky Way galaxy. It continues to race toward Earth. When it's 100 light years away, a guy named Albert Einstein writes down equations that suggest there could be these gravitational waves, unknown that one is already racing toward the planet, and it continues to race onward. 2 light days. It's 2 light days away when they turn on the newly refined version of the LIGO detector, and 2 days later that wave rolls by planet Earth, shakes the 2 detectors, one in Louisiana, the other in Washington State, giving us the first direct detection of ripples in the fabric of space. So these things are out there. And before the direct radio telescopic imagery from the Event Horizon Telescope of the black hole in M87, that ripple in the fabric of space was the most direct evidence that black holes are real, because when you took the way that the machine in Louisiana and Washington, it twitched for just a tiny fraction of a second, when you figured out using supercomputers what the cause of the wave must have been, you are led to 2 black holes that are 28 and 31 times the mass of the sun. And that was the only explanation for the data. And so there's this beautiful indirect proof that these stellar-sized black holes are actually out there. And then, of course, we take a photograph of one in a nearby galaxy.